Find the critical oxygen deficit, D sub C, in milligrams per liter. In this problem, the effluent from a wastewater plant discharges into a local stream. The flow rates, temperatures, 5-day carbonaceous biochemical oxygen demand at 20 degrees Celsius, and the dissolved oxygen values are provided. The deoxygenation rate constant and reoxygenation rate constant are also provided in base E at 20 degrees Celsius. The critical oxygen deficit in milligrams per liter equals the deoxygenation rate constant, K sub D, in days to the minus 1, times the ultimate BOD in milligrams per liter, divided by the reoxygenation rate constant, K sub R, in days to the minus 1, times E raised to the negative 1 times the deoxygenation rate constant times the critical time, T sub C, in days. The problem statement already provides the oxygenation rate constants, K sub D and K sub R, but we do not know the values of the ultimate BOD or the critical time. We'll first solve for the ultimate BOD. The ultimate BOD in milligrams per liter equals the BOD at a given time period, T, in milligrams per liter, divided by 1 minus E raised to the minus 1 times K sub D times the time, T, in days. Since we've been given the data for 5-day BOD, we'll use a time of 5 days. Next, we'll calculate the 5-day BOD in the stream after it mixes with the wastewater effluent in milligrams per liter. The 5-day BOD after mixing equals the weighted average of the 5-day BOD values of the two water bodies based on their flow rates. The known values are plugged into the equation, and the 5-day BOD of the two water bodies equals 5.77 milligrams per liter. Returning to our equation for the ultimate BOD, the known variables are plugged in, and the ultimate BOD equals 9.13 milligrams per liter. Now that the ultimate BOD is calculated, the last unknown variable is the critical time. On an oxygen sag curve, the concentration of dissolved oxygen initially decreases and then rebounds back based on the Streeter-Phelps equation, which involves the rate constants, the ultimate BOD, and the initial oxygen deficit. D sub C is the critical deficit when the dissolved oxygen is at its minimum value, which we're trying to solve for and which occurs at the critical time, T sub C. The critical time in days is a function of the oxygenation rate constants, the initial oxygen deficit, and the ultimate biochemical oxygen demand. The only unknown variable is the initial oxygen deficit, D sub O, in milligrams per liter. To determine the initial oxygen deficit, we'll subtract the initial concentration of dissolved oxygen from the initial saturated concentration of dissolved oxygen for the combined flows. The initial concentration of dissolved oxygen is the weighted average of the initial concentrations of dissolved oxygen from the two water bodies, weighted by flow rate. The values are plugged into the equation, and the initial dissolved oxygen concentration equals 7.73 milligrams per liter. The saturated dissolved oxygen concentration is calculated the same way, where the flow rates are plugged in, and the saturated DO concentrations are a function of the temperature of each body of water. Assuming no chloride contamination, the saturated DO concentrations are 9.13 milligrams per liter and 10.15 milligrams per liter for the wastewater effluent and the stream, respectively. The initial saturated dissolved oxygen concentration equals 10.11 milligrams per liter. By knowing the initial DO concentrations and the initial saturated DO concentration, the initial oxygen deficit in the stream equals 2.38 milligrams per liter. At this point, we can return to our equation for the critical time, T sub c. Since we know the initial oxygen deficit is 2.38 milligrams per liter, and we plug in the oxygenation rate constants and the ultimate BOD, the critical time equals 2.66 days. The value of 2.66 days is plugged into T sub c as well as the other variables, and the critical oxygen deficit equals 3.57 milligrams per liter. When reviewing the possible solutions, the answer is C.